constant 1. What is this constant 1? It is 1, 1, 1, 1 from minus infinity to plus infinity. It is a sampled version of u of t. So the Fourier transform becomes periodic, 2 pi delta omega periodic after every 2 pi. So it becomes summation of 2 pi delta omega plus 2 pi k. Un is unit step sampled sequence. What is the Fourier transform of unit step function in the continuous Fourier transform in the continuous domain? It was 1 by j omega plus pi times delta omega. So here that 1 by j omega becomes 1 by 1 minus e to the power j omega, and 1 by 1 minus e to the power j omega is a periodic function. But if you write only pi delta omega, then it does not remain periodic. So you have to add delta omega at every 2 pi. So it is pi times summation of delta omega plus 2 pi k. So it was 1 by j omega plus pi delta omega, that was the Fourier transform of u of t. Sampled version will have the periodic counterpart. 1 by j omega is replaced by 1 by 1 minus e to the power minus j omega plus pi times summation of delta omega plus 2 pi k. E to the power j omega n, j omega 0 n. This is the Fourier transform of this can be found out from Fourier transform of 1. So take Fourier transform of 1 and then apply your modulation property to find out that it is 2 pi delta omega minus omega 0 plus 2 pi k. Alright. Then alpha to the power n un for mod alpha less than 1, yesterday we have seen. N plus 1 a to the power n un also can be seen. It is yesterday we have seen the property j times dx omega divided by d omega. This also can be found out easily. The last one we will prove now. Last one we will prove now. You might have realized, imagined that what is this h LP e to the power j omega? What could be that? How do you name this? Okay, what is this? It is a frequency transform. H, capital H means it must be the Fourier transform of small h. What is small h noted in continuous continuous domain? Impulse response. Fourier transform of impulse response is frequency response. So h LP e to the power j omega is a frequency response of a low pass filter. Frequency response of a low pass filter, and this h LP n here, this is the impulse response of the low pass filter, ideal low pass filter. Alright, this we will prove just now. Is it okay? Have you noted down all? So now plot the second one. Plot this HLP. I want you to plot this function first. Plot this function. I will rewrite it here. H LP e to the power j omega is equal to constant 1 for 0 less than equal to omega mod less than omega c, and omega c less than mod omega less than equal to pi. Plot this. When I want you to plot this, it is very simple. We know that it is Fourier transform of some discrete sequence h of n. It means it exists from only minus pi to plus pi. So it exists from minus pi to plus pi. There is a component called a variable called omega c, which is known as a discrete time cutoff frequency, small omega c. So cutoff frequency minus omega c plus omega c, and then between minus omega c to plus omega c it is constant 1. Between minus omega c to plus omega c, this mod omega makes it minus plus. Actually, what is this? How is this converted? This is converted to minus omega c less than equal to omega less than equal to plus omega c. How will this converted to? This will be converted to omega c less than equal to less than omega less than equal to pi and minus pi less than omega less than equal to minus omega c. This is the second condition. This is the first condition. I wanted you, when I said plot this, it means I wanted you to understand these two concepts. All right. Now, yesterday we have seen that this is a periodic function. Every periodic function can be represented by in its Fourier series form, but this is a reverse Fourier series, inverse Fourier series. What is the Fourier series? Inverse Fourier series. Why I am saying this as inverse Fourier series? Because it is a periodic function in the frequency domain. We have studied Fourier series in the time domain. Every periodicity in the time domain was represented by a sequence of numbers in the frequency domain. It is exactly opposite of that. It is exactly dual of that. So now we can find out. So h of LP n will be equal to 1 upon 2 pi period integration minus pi to plus pi h LP e to the power j omega e to the power j omega n d omega. We will prove this also in a moment. The algebraic proof of it also can be given. Now here this becomes 1 by 2 pi. What is this? This becomes minus omega c to plus omega c constant 1 e to the power j omega n d omega, which is equal to 1 upon 2 pi e to the power j omega n divided by j n from limits minus omega c to plus omega c. This can be written as 1 by 2 pi n. I will only write pi n, 2 I will take here. What is this? It is e to the power j omega c n minus e to the power minus j omega c n. J also is remaining, so 2j. This becomes equal to 1 upon pi n times twice j sine of, or I can write directly sine of omega c n, which means this is 1 upon pi n times or sine of omega c n divided by pi n. How can I write this further? Further it can be written as omega c by pi multiplied by sine of omega c n divided by omega c n. So this is a sinc function. The function given was in frequency domain. What did we do here? We have actually determined inverse Fourier transform, inverse discrete time Fourier transform. This is an expression for inverse discrete time Fourier transform. Using that, we have found out the sequence for which this is the Fourier transform. All right. Is it okay? whatever we have seen just now was a proof of Fourier inverse of HLP e to the power j omega is equal to HLPn. This also implies that Fourier transform of HLPn is equal to capital HLP e to the power j omega, which means whatever we have proved is Fourier transform of sine of omega Cn divided by pi n is constant 1 for 0 less than equal to mod omega less than omega c or less than equal to mod omega c, 0 for omega c less than mod omega less than pi, less than equal to pi. Alright. So, it is similar to our rect function. Rect function, what we defined in the continuous time systems or continuous Fourier transform, had a Fourier transform which is a continuous rect function in the time domain, had a Fourier transform which was sinc, and we used duality property to prove that Fourier transform of a sinc is a rect function. Alright. Let us prove the inverse Fourier transform relation. What was the relation we derived? We said we started with x e to the power j omega is equal to summation of x of n into e to the power minus j omega n, n going from minus infinity to plus infinity. Let us multiply this both sides by e to the power minus j omega k plus j omega k and integrate from minus pi to plus pi, because this function is existing only from minus pi to plus pi. So, what happens? X e to the power j omega e to the power j omega k integration from minus pi to plus pi is equal to summation n going from minus infinity to plus infinity xn e to the power minus j omega n minus k. I have skipped one step. E to the power j omega k was absorbed in this. This is e to the power minus j omega into minus k is e to the power plus j omega k. N minus k is going to be an integer all the time. N minus k is going to be an integer all the time. Let us observe what is the value of this summation for n minus k is equal to 0 and for n minus k not equal to 0. It is not very important to prove this. For me, I am taking this proof only because I want you to understand the function summation of e to the power minus j omega n minus k for these two purposes, for these two values of n minus k. Can you find out this? I want you to find out the summation of xn multiplied by e to the power minus j omega n minus k for n minus k equal to 0 and for n minus k equal to not equal to 0. Where minus pi to plus pi? I am sorry, I made a mistake. The integration of minus pi to plus pi is missing on the right hand side, which you please add. It can be added here, but I can interchange summation and integration, and xn is independent of that integration. So it becomes integration minus pi to plus pi. So I want you to understand integration of minus pi to plus pi, this value. So what is it? I want you to know what is the value of integration minus pi to plus pi e to the power minus j omega n minus k d omega. This will be equal to, when n minus k is 0, it is easy. When n minus k is 0, it is 1. 1 in the range of minus pi to plus pi. So what is the value? This is equal to 2 pi for n minus k is equal to 0. It means for n is equal to k. This implies when n is equal to k, the value is equal to 2 pi. What is it going to be for n minus k not equal to 0? Is an important question. When n minus k is non-zero. So what is e to the power minus j omega? Find out that. Take some value, some non-zero value of n minus k. Say n minus k equal to 1. So what is it? It's e to the power minus j omega from minus pi to plus pi. So e to the power minus j omega divided by minus j in the range of minus pi to plus pi. So e to the power minus j pi minus e to the power minus j pi divided by minus j. So it becomes twice sine of omega or twice sine of pi, and sine of pi is 0. When you take k, n minus k equal to 2, it becomes sine of 2 pi, 0. So all sines of pi, 2 pi, integers, whether n minus k is plus 1, plus 2, plus 3, plus 4, plus 5, plus infinity, or minus 1, minus 2, minus 3, minus 4, all these cases, this function is going to be 0. So I can write this function is 0 for n not equal to k. Alright? N not equal to k, and thus substituting this result here, the summation k is any value between minus infinity to plus infinity. Alright, k is any value between minus infinity to plus infinity. So when I write this value is going to be equal to 0 for all values of n minus k not equal to 0, or it means n not equal to k, it times it is going to be 0. That means this summation will have 0 value. The summation will be non-zero only when n is equal to k. So what is the right hand side going to be? Right hand side going to be, this side is going to be this right hand side of this equation. So it is integration minus pi to plus pi x e to the power j omega e to the power j omega k d omega is equal to 2 pi times small x of k. Are you with me? Summation of xn multiplied by integration minus pi to plus pi e to the power minus j omega n minus k d omega, n going from minus infinity to plus infinity. This value is going to be equal to 2 pi times x of k. Is that clear? Because this value is going to be equal to 0 for n not equal to k. That means it is only non-zero for n equal to k. So in this I replace n is equal to k, that is all. So only one value in this summation exists. What is that one value? It is x of k. X of n for n equal to k or x of k. That is why I can write like this. So from here I can write x of k is equal to 1 upon 2 pi integration minus pi to plus pi x of e to the power j omega e to the power j omega k d omega. Friends, remember n is also integer, k is also integer. So it doesn't matter whether you replace it by n or k. So that's the algebraic proof. Yesterday we have seen logical proof. A periodic function can be expressed in the form of Fourier series, but there it was a periodic function in the frequency domain was represented by this. So that was a logical proof. This is the algebraic proof. Alright, and here I can write x of k is what? It is identified or denoted as Fourier inverse of x e to the power j omega. Now both the relations are there with us. I will rewrite those relations. X of e to the power j omega is equal to summation of x of n e to the power minus j omega n, n going from minus infinity to plus infinity, has a counterpart. This is analysis equation and this is synthesis equation. What is the synthesis equation? X of n is equal to 1 upon 2 pi integration minus pi to plus pi x e to the power j omega e to the power j omega n d omega. Compare this with CFT equation. What was the CFT equation? X of j omega is equal to integration x of t e to the power minus j omega t dt minus infinity to plus infinity. Similarly, we had x of t is equal to 1 upon 2 pi integration minus infinity to plus infinity x of j omega e to the power plus j omega t d omega. Relations are almost the same except for the change of meaning of frequencies. Capital omega is small omega by t, or small omega is capital omega times t, except that there is no change in the equation. You see here, when you take a Fourier transform of a continuous time signal, you multiply that by infinite set of orthogonal basis functions, complex exponentials, in the form of e to the power minus j omega t, xt multiply by this infinite set of complex exponentials and integrate over minus infinity to plus infinity, because xt exists from minus infinity to plus infinity. Same process is applied here, except that xt becomes discrete. In case of continuous time, because it is continuous time, I integrate. Because it is discrete time here, I sum. I make use of summation. Integration and summation is the same. Even if I integrate xn, the meaning is going to be the same. Here also I am multiplying this xn by complex exponential, infinite dimension complex exponential, but here the infinite dimension is e to the power minus j small omega n, where small omega is capital omega times capital T, which was sampling interval. The relationship was capital omega times t is equal to small omega. These are also infinite set. What is infinite in this? Omega. Omega is in the range of minus pi to plus pi, is continuous, and there is this omega is uncountably infinite, from minus pi to plus pi uncountably infinite. Here omega is minus infinity to plus infinity, uncountably infinite again. So both are not computable by a digital computer. This equation you cannot compute by using a digital computer, although we are doing it in the form of an approximation. Alright? Is it clear? Understanding with continuous Fourier transform and this? So Fourier transform is a more general transform. Whether you apply it for continuous time or discrete time, the function is going to be the same, with minor modifications in the variables used. That's all. Is it okay? Any questions so far? Before going to convolution, we will once again switch over to discrete time systems. Alright. For certain about 10 minutes we will talk about discrete time systems, how they are governed, what is the governing equation, and how do we come across what is known as linear convolution sum. Then only we will be able to take its Fourier transform, right. Discrete time systems. What is a discrete time system? It is a black box with now the input and output becomes only discrete in time. So, x of input is represented by x of n, output is represented by y of n, and what is this black box doing? It is processing the input signal to produce the output signal yn. So, it is going to be a transformation applied on x of n. This dot is x of n. Transformation applied on input gives you output. So, y of n is transformation applied on x of n. Now, we declare the transformations. What are the transformations likely? So, transformation T dot is linear. I do not need to talk about this again. What does it mean? It means if the input is a linear combination of inputs, the output also will be linear combination of the outputs. Alright. So, linear, that I will write for the sake of completeness here, transformation applied on alpha 1 x1 n plus alpha 2 x2 n will be equal to alpha 1 y1 n plus alpha 2 y2 n. Assuming that y1 comma 2 n is equal to transformation applied on x1 comma 2 n. This means y1 n is the output of x1 n, y2 n is the output of x2 n. Assuming this is true, then the transformation is linear. The transformation also can be time invariant. Transformation can be time invariant. What is the time invariant transformation? Transformation applied on a delayed input x of n minus n0. Transformation applied on x of n minus n0, if it is equal to y of n minus n0, then the system is time invariant, time or shift invariant. Here it is shift, otherwise it is going to be time varying or shift varying. The same examples will be valid. Whatever examples we took for continuous time systems are valid here as well. For example, y of n is equal to alpha times x of n plus beta is a non-linear system. Y of n is equal to alpha times xn is going to be linear. Y of n is equal to alpha times e to the power xn is going to be non-linear. Y of n is equal to summation of alpha k into x of n minus k, k going from minus m to plus m, where m is constant, is going to be a linear system. The examples of time invariant systems, y of n is equal to e to the power x of n is an example of time invariant system, because y of n minus n0 is same as e to the power x of n minus n0. Y of n is equal to x of 2n is an example of time varying system. Is it okay? Any question on this? Perspective. Discrete time systems could be obtained from a continuous time counterpart. We are likely to convert a discrete time system into a continuous time system into a discrete time system. We have seen that a continuous time system can be governed by a governing equation, which is a linear constant coefficient differential equation. What is the differential equation? It could be something like d summation of some ak times dk yt by dt k going from say 0 to capital N was equal to summation of k going from 0 to m bk times dk xt by dt k. This we wrote as a linear constant coefficient differential equation, which is a governing equation for a continuous time systems. If I want to convert this differential equation into a equation for a discrete time system, what is being done? Try to understand how do you write dy by dt, or for that matter dx by dt. How do we write this? How is this defined? Dy by dt is defined. For example, if you have some dy here, y as a function of x, this is y on this side, it is a function of x, on this you have x. How do you define dy by dx? Dy by dx is defined as, you take two consecutive points x1 x2 and you get 2 consecutive points here y2 and y1. Then in the limiting sense, what do? Limit x or delta x tends to 0. Limit delta x tends to 0. What is delta x? So delta y, I write this as delta y by delta x, this as delta x. This tends to dy by dx. This is a continuous function, this is a discrete function. What is delta x? It is x2 minus x1. What is this? It is y2 minus y1. Alright. So if you write in general, if suppose this is x, so it basically it's what? Next value minus previous value. If I treat this as x of n, what will this be? X of n minus 1. What is, if this is treated as y of n, what is this going to be treated as? Y of n minus 1. So in general, I can write dy by dt. Now here it is a function of time t, and what is t2 minus t1 or tn minus 1? It is going to be capital T, it is going to be 1. So I forget about that, and then I write dy by dt as y of n minus y of n minus 1. Alright, nth value minus n minus 1th value. How do you write d2y by dt2? Can you tell me? It is d of this minus d of this. So how that can be written as? Y of n can be written as y of n minus y of n minus 1, and y of n minus 1 can be written as y of n minus 1 minus y of n minus 2. So that minus minus becomes plus. So overall it is d2y by dt2 is yn minus twice yn minus 1 plus yn minus 2. So all these differentials can be written in the form of differences, and it becomes a difference equation. A governing equation becomes a difference equation. That equation is called as linear constant coefficient difference equation. What will be the form of it? It will always have, I hope if you have done a course on numerical methods, in which you have already done that. Did you do a course on numerical methods? Difference equations you have done. You have done the formulations, interpolation formulas. In that you have used 3 different types of differences. What were they? Forward difference. Can you write what is forward difference? Forward difference is y of n plus 1 minus y of n is a forward difference. Y of n minus y of n minus 1 is a backward difference. And the third one is central difference. What is it? Y of n plus half minus y of n minus half. This is central difference. Huh? I couldn't get. What is it? Is it right? If that is right, why am I not choosing forward differences? Why I am not choosing central differences? I am only choosing backward differences. Because of causality. Very right. Because of causality, yn plus 1 is not causal, hence realizable. Yn plus half, it is a sampling interval which is 1. Half sample delays, not realizable directly. Alright? That is why I have used only backward differences, because it is realizable in real time. This could be realizable in offline, when the data recorded is already present and I am moving n wherever I want. Alright? When pre-recorded data is available and I am choosing some point of time for processing, the samples that are n plus 1, n plus 2, n plus 3 are available to me. Alright? And that is realizable in offline. When that is possible, when it is a pre-recorded data is available with me and I am processing a pre-recorded data, that time yn plus 1 is realizable. So in general, this equation becomes this differential equation becomes summation of, I'll make dash here because I want to use same ak and bk for difference equation also. I am using ak dash here. So you combine all yns, you combine all yn minus 1, combine all yn minus 2 and so on. How many differences will be there? For n equal to 1, that means for k equal to 1, dy by dt you have one difference. You have one value of yn and one value of yn minus 1. When you take 2, you have three values, yn minus 1 and yn minus 2. Last value is 2. When you have third differential of order 3, you will have 4 different values, yn minus 1, yn minus 2, yn minus 3 and so on. Like this, if you have the summation here is nth, 0 to n. So we have nth order differential which will be converted to nth order difference. So what is the difference? I can write it as, I combine all yns, yn minus 1, yn minus 2. How many such things will be there? N minus capital N. So ak times y of n minus capital N, I am sorry, k, once again 0 to n going from, so k going from 0 to capital N is equal to summation of k going from 0 to m bk times, this bk dash and bk is different, alright, because yn minus 1, second time you have yn minus twice yn minus 1 plus yn minus 2 and so on. So you have yns combined, they will be different than this ak dash. So I am writing that value of yn, coefficient of y of n when k equal to 0. K equal to 0 is a0. This a0 and a0 dash are going to be different. bk times x of n minus k, and this is called linear constant coefficient difference equation. So the governing equation for a discrete time system is something like this. However, it is not written in this form. The form used for writing difference equation of a discrete time system is going to be like this. So I write this as a0 times y of k, y of n, I am sorry, plus summation of k going from 1 to n, ak times y of n minus k is equal to summation of bk times x of n minus k, k going from 0 to m. Then I write a0 times y of n is equal to summation of k going from 0 to m ak times y of n minus k minus, I am sorry, this is minus and plus summation of bk times x of n minus k, k going from 0 to, this is n, this is 1 to n and this is 0 to m. Then I take this a0 on this other side. So this becomes ak by a0, this becomes bk by a0. Now what happens? This can be written as y of n is equal to, I write this first, summation of k going from 0 to m. I define this as some dk, dk times x of n minus k, where this is my dk, minus summation of, I define this as ck, ck times y of n minus k, k going from 0 to n, 1 to n. Now read this equation. How do you read this equation? What is xn? So it is in general, it's d0 times xn plus d1 times x of n minus 1 plus d2 times x of n minus 2 plus and so on, plus dn times or dm times x of n minus m minus c1 y n minus 1 minus c2 y n minus 2 and so on, minus cn y of n minus n. So now can you read this? What is yn? Yn is present output. Present output is a combination of present input, linear combination of present input, past input, past input, past input, m past inputs, present input, m past inputs and n past outputs. So present output is a function of present and past inputs and past outputs. Which is what we want. We want output of any system to be a function of something, and this clearly defines the input output relationship for a discrete time system, which is very, very important. So discrete time systems are all governed by some similar difference equations. Any question? Any question? Take your time in understanding this. We have linear constant coefficient differential equation in the form of k going from 0 to n, some ak dash into dk yt by dtk is equal to summation of some bk dash dk xt by dtk, k going from 0 to m. This is a linear combination of differentials. So what we get when we discretize the system is going to be linear combination of differences. So differences will always have terms like yn, yn minus 1, yn minus 2 and so on. So this will be a linear combination of a different, this constants and the other constants in the difference equation will be different, because there is a usual process of converting a differential into difference. You have two terms in first differential. First order differential will have two terms, yn and yn minus 1. Second order differential will have three terms, yn, yn minus 1, yn plus yn minus 2 and so on. When you combine all these with scaling like this, linear combination of all these will result into a function of yn, yn minus 1, yn minus 2 and so on up to yn minus capital N with different coefficients. So that can be represented by some ak times. Now these ak are different than what is used in the earlier derivation. So instead of that, let me write directly the final form. Summation of y of n is equal to summation of k going from 0 to m bk times x of n minus k minus summation of k is equal to 1 to n times ak times y of n minus k. Instead of ck dk, I have replaced it by bk ak again. Alright. So this is a form which is a popular form for representing difference equation. This is linear constant coefficient difference equation. Why are we doing this? Because now we are covering discrete time systems. We wanted to find out what is going to be a generalized equation, governing equation for discrete time systems, and that we have obtained from its continuous time counterpart. Converted a differential equation into a difference equation by using backward difference, by replacing the differential by a backward difference, because backward difference is realizable in real time. Other possibilities of differences are non-realizable in real time, hence it is non-realizable. So this is very important. All right. So is this clear? This is a governing equation for any discrete time system wherein the output, present output, is a function of present and past inputs and past outputs. K equal to 1 makes this past. Alright. Turning back our attention to linear time invariant systems. We have seen linear systems, we have seen time invariant system. Now let us combine the two. Now while doing so, we need to write a generalized xn. Xn will be equal to, it can be written in a generalized form as x of k times delta n minus k, k going from minus infinity to plus infinity. How to write this? For example, you have some values like this 1, 2, 3. If this is my xn, how do I write this xn as? X of n is equal to 1 times delta n minus 1 plus 2 times delta n minus 2 plus 3 times delta n minus 3. Can I write like this? So if it is an infinite duration sequence, then it can be written as minus infinity to plus infinity. This xk is the values, sk are the values of those sequence values, and delta n minus k decides the location of that sequence value. So if this sequence xn can be represented like this, a generalized sequence xn can be represented by this, where x0, x1, x2, x minus 1, x minus 2 are the values of this sequence, and delta decides the location of that value. Equivalently, if you recollect, we have also written x of t as integration minus infinity to plus infinity x of tau delta t minus tau d tau. Same. This is with reference to continuous time system, this is with reference to discrete time. Any question? Now, to this equation, we apply y of n is equal to transformation applied on x of n. Now define this transformation to be linear. Assume that t dot is linear, then what happens? Y of n becomes transformation applied on summation of k going from minus infinity to plus infinity x of k into delta n minus k. Transformation is linear, so this becomes transformation applied on summation is summation of transformations. So I can interchange that, summation k going from minus infinity to plus infinity, x of k is a constant for respective things, and then transformation applied on delta n minus k. This is equal to, now say that T dot is time invariant. Define T dot as time invariant. That means I am combining linearity with time invariance. And before going ahead, I define h of n to be defined as transformation of delta n. And because the system is time invariant, I always get h of n minus k as response to delta n minus k. That means when I say that T dot is time invariant, y of n can be written as summation of x of k times transformation is now time invariant. So T of delta n minus k is written as h of n minus k. K going from minus infinity to plus infinity. This is defined as xn convolution with h of n, and this convolution symbol now with reference to discrete time system represents a convolution sum. Convolution sum are also called as linear convolution. In continuous time case, there was only one convolution, which is called convolution integral. In case of discrete time system, there are two different convolutions. Hence, we have to name this convolution as linear convolution because it is an impact, it is an effect of linearity applied on systems. Because this is applied to linear systems, I have to call this as linear convolution. But linear convolution sum, with reference to continuous time systems, it was convolution integral. Here it becomes convolution sum. If you once again compare our equation of convolution integral, this is what is convolution integral. This is applied for continuous functions. Two functions are continuous, whereas here two functions are discrete. We will see the differences between these two. There are minor differences between these two. Okay. First, we will try to understand what is this convolution summation. All right.